Thank you for the introduction and good afternoon to everyone. Thank you also for the opportunity of being here, sharing our work on density functional theory for superconductor and our implementation in the SIESTA code. So today I would like to introduce you through the SIESTA-BdG method, both the theory and the implementation. Then we will look at the results and the code validation, where we will apply this method to study both conventional and unconventional superconductors. I will also briefly discuss about an efficient algorithm for sampling the density of states for these systems. And later we will apply this method for more involved systems, such as heterostructure, where we will show that it is possible to induce superconductivity in such lead-red-lead heterostructure. And I will also delve into a discussion on the requirements for Majorana Zero modes. And lastly, I will, as an outlook, introduce what we did as a proof of concept to use our method for superconducting quantum transport. And without further ado, when we think of a normal metal, we think of electrons as repelling each other. However, we very well know that in unconventional superconductors, this naively picture falls off, simply because superconductivity is a quantum phenomena that shows up at the macroscopic scale, and the electron-electron interaction mediated by the BCS or phonon vibration leads to the formation of Cooper pairs, and you have collective motion without scattering, which leads to the current flowing, dissipationless current flow. However, in conventional superconductors, all of this happens at very low temperature, which, if we think in terms of device, might not be useful for application in real life. On the other side, we also know that by now there are signs or evidence of unconventional superconductivity, superconductivity that can work also at a higher temperature. However, the macroscopic mechanism behind unconventional superconductivity are not well understood. And here in this slide, you can see a few examples of unconventional superconductivity, which might come either from the complicated dispersion or fermiology of the electronic states near the Fermi level. So we have this band nesting effect, or maybe through the correlation of the electron is not coming simply by the usual Coulomb electron-electron interaction. It's actually related to the twisting, as in twisted layer graphene. And also there is an interplay between disorder and dimensionality. And lastly, we will also mention the topological superconductivity, which is yet another phenomenon, which I will present later on when I will discuss about the lead-red-lead heterostructure. So we have a complex phenomena. It is still not fully understood. And the question is now, how can we use density functional theory and our modeling techniques to understand such a phenomenon? So the way that we start is with density functional theory, and this you all know very well. We describe the system with an Hamiltonian, which contains the kinetic energy, the electron-nuclei interaction, and the electron-electron interaction. And then when we think about the superconducting pairing, we introduce a pairing where now an electron that is passing through the lattice is creating a net positive attraction, leading to the formation of Cooper pair. And this is how we form, and this we refer to the superconducting pairing. So DFT is useful for because it allows us to have a fully capture the quantum nature of atomistic interaction. So we have a proper geometrical description, and we can include all sorts of effects. And we have in density functional theory a given wave function and given Hamiltonian. What we do within superconductivity is that we exploit the Bogoliubov formalism, which is a formalism that allows to unify the treatment of both the normal and superconducting properties, and also to model the superconducting pairing beyond BCS. And the way that we do it is by doubling the degree of freedom. So now the electronic wave function becomes a number spinor, and we have an electron hole component, and the Hamiltonian is paired or doubled in a new Hamiltonian, which is the Bogoliubov Hamiltonian, where along the diagonal we have the usual electronic and hole Hamiltonian, and this is minus the complex conjugate of the electronic one, because it's the whole Hamiltonian. And then we have these off-diagonal terms, delta, which are the pairing potential, which encode the superconductivity interaction. And it's the coupling between the electron and the hole. So just to go deeper into the theory, here on the left, we have the usual Kohn-Sham density functional theory, and on the right, the Kohn-Sham Bogoliubov equation. So while the usual Hamiltonian with T and the potential is replaced by a new set of equation with, and now we do have a new term, which is the delta, the pairing potential, which indeed couples a set of equation for the electron and the hole, U and V. And then the way that this is done is that we replace the effective single particle potential with a new potential and also exchange correlation function. And now everything is expressed not only in terms of the normal charge density rho, but also in terms of the anomalous charge density chi. And the rest follow very closely to the usual density functional theory way. However, our new exchange correlation function is quite of a complicated object, because it is basically a four-dependent, well, it is a function both of rho and chi, but it is also a four-point function of four different spatial coordinates. And as you can imagine, this is very difficult to integrate. And therefore, what we do is that we apply a very well-known approximation given by Suvasini called the local approximation, where now the pairing potential can simply be expressed in terms of a semi-phenomenological parameter lambda and chi. And now chi is local, depends only on one spatial coordinates. I mentioned that lambda is a semi-phenomenological parameter, and the way that we can obtain this parameter is either by employing other fully initial density functional theory techniques, for example, based on electron-phonon interaction from the experiment, or we can model it. And here I would like just to mention and acknowledge other codes that implemented a similar formalism based on superconducting density functional theory. For example, ELK and EPW, their code mainly focused on a fully ab initio and microscopic description of superconductivity. However, they are mainly focusing on electron-phonon interaction, therefore only on conventional superconductivity. They can treat a relatively small system, while in the case with approach of the SIESTA-BdG method, which has also been implemented by in a similar way by UJR codes and Questal. The main advantage is that we can also model a conventional superconductivity, and that we can go to larger system. And the idea is that this method will work as a bridge between the models and microscopic theories. Still on the method, we have the workflow, the way that this works, that we start with a density functional theory calculation, and then we asked ourselves, we implemented actually 3 different levels of accuracy, which we named the non-SCF-BdG, fixed delta, and full SCF-BdG. And the 3 different solution methods differs in the level of self-consistency reached in the on the electron Hamiltonian or on chi, or both in the electron and the Bogoliubov Hamiltonian, which is quite complicated to say, but the workflow might help. So we can either read the electronic Hamiltonian directly from density functional theory and then skip the self-consistency loop over the anomalous quantities and directly solve the Bogoliubov equation, where now delta are just numbers and they've not been updated via the SCF cycles. And then we can compute all our post-processing quantities as the superconducting dose and the bands, or we can go inside the loop where we update self-consistently either only delta in the fixed delta method, or at the same time the Kohn-Sham, the electronic Hamiltonian and delta in the full SCF-BdG method. And clearly this is done to allow the user for the freedom, to explore also computationally expensive or computationally less expensive simulations. Also, the way that we initialize delta, the pairing potential, we have implemented in two different ways. We can either couple directly the orbitals, basically in a basis of reciprocal space way like as matrix elements, or we can also model the superconducting pairing potential in real space as a sum of Hardwell function or plane waves or few other options. So all of this, and if you are interested in more details about the method and implementation, it has been recently published on PRB by us. And let's move to the code validation and the results. So we start with bulk niobium, which is a very well-known conventional superconductors. And these results were obtained by a colleague and of us, Arnold, which computed the superconducting density of state with the SIESTA code in blue and compared with the UTHR code, which also exploit a similar methodology to compute the superconducting dose and the experiment. So first of all, we recovered the conventional U-shaped density of state, typical of conventional superconductors. This is good. And then we also have an agreement with the UTHR code that is also checked and with the experiment. Moreover, if we look at the superconducting band structure, we nicely retrieve the particle symmetry, and this is more of a check. If we were to zoom in close to the Fermi level, we see that we have this electron hole symmetry, where the electron is now depicted in red, and the hole, we have the weight on in blue. And also the degree of hybridization close to the superconducting gap is given by this weighted factor for delta. Now, the way that we specify, I already mentioned that we can specify delta, the pairing potential in real space. And for example, we can, if you look at the unit cell of bulk niobium, we can either specify it as a constant. So, and then, so for example, if we were to specify the parameter lambda as a constant all over the unit cell, then we can compute delta and chi, and then we see that the resulting shape of the superconducting pairing potential is very well localized close to the atom here on the edge, and it looks almost like a bond. And so this is it allows us to explore or have a visualization of the superconducting pairing potential after at the end of our simulation. And we can also use actually these touching spheres Hardwell's initialization of the pairing potential, which in our experience is actually the one that works the best for conventional superconductors, or actually in general. And lastly, there is also the Gaussian initialization, which allows you to have a very localized superconducting pairing potential in space. Okay, so once we do this, I want to spend some other words and technicalities on the way that we compute this superconducting density of states. So first of all, I have to mention that we include spin-orbit coupling, which is important in the light of studying, for example, topological materials, but not only. And something that we discovered while developing the method is that, well, of course, the electronic temperature has to be really low in order to sample such a very narrow energy range, because typically the superconducting gap is of the order of a few millielectron volts. But this also implies that we need a very high K-mesh or K-sampling for the p-dose. And here on the right, you can see that if you were to use only a 100 by 100 K-mesh, the results are very noisy. While when we go towards 800 cube, the superconducting density of state starts to converge. Okay, so we had to deal with this issue, and the way that we solve the issue of the computational expensive simulation is that this is an idea and work done by Arnold. So the way that we do it is that we have the adaptive brilliance on sampling technique, where now the way that the code works is that if you imagine your grid as a collection of points, then the algorithm computes for all these K points the eigenvalues and looks only at the contributing points in the grid. And for each of the contributing points, it creates a subgrid which can be a 2x2, a 3x3, or 4x4, depending on it's an input flag, so you can choose. And then you iterate until you find only the points that are really meaningful close to the Fermi level, and therefore allowing you to sample only close to the Fermi level where you are actually interested. And this speed up the simulation quite a lot. And there I just showed that the methods work. So we compared the superconducting density state computed with the uniform grid and with the adaptive grid. So we gained a lot in terms of time and computational efficiency while retaining the shape and the magnitude of the superconducting gap. Now, moving towards unconventional superconductors. We applied our method on bulk iron cyanide, and bulk iron cyanide is quite a complicated material. First of all, it has different magnetic configuration. We can either have the staggered dimer or the null phase, and the null phase is an antiferromagnetic phase, and it is focusing on the null phase, we computed the superconducting density state, and then we saw that we retrieved this V-shaped dose, which is typical of unconventional superconductors. And in order to gain more insight into the system, we can exploit one of the initialization method of SIESTA-BdG, which is the orbital initialization method, where we can specify the superconducting pairing potential delta, mini, directly in terms of the atomic orbitals. So we can have either an intra-orbital coupling, where we have the coupling only between or on the same atom and the same orbital, or the on-site coupling, where we have the superconducting coupling on the same atom and on different orbitals, or a full overlap coupling where we couple everything. And those are three regimes, but we can actually do, we have complete freedom actually to couple what we want. And in this way, we can selectively couple superconductivity only on specific orbitals. And in this way, we were able to analyze the superconducting dose of bulk iron selenide and see the contribution to the superconducting dose only of specific orbitals. So the dxy, dxz zeta, dy zeta, d zeta square, and dx square minus y square. And then by performing the simulation, we understood that the superconductivity for bulk iron selenide comes from the x zeta and the y zeta orbitals. So we have some out-of-plane components, and this is also checked out with the experiment. And then we don't have any superconducting pairing gap if the pairing is restricted to other orbitals, 3D orbitals. We can then move to lower dimensionality and look at iron selenide monolayer. Now, when we compute the superconducting properties for iron selenide monolayer, always in the null phase, so in this antiferromagnetic phase, we can look at the superconducting band structure, which is quite interesting because now the particle symmetry in such a way that it shows anisotropy in the electron hole components, so the red and the blue here. And then when we look at the density of state, we find two superconducting gap instead of one, as usual, which are 12.4 millielectron volt and 4.6 millielectron volt. Moreover, we see that if we were to project the superconducting density state only over the electron, the whole component, we also see a strong anisotropy in the shape and in the intensity of the dose in B. And then we can project over a specific atom to discover that superconductivity originates mainly from the iron atoms. And among the iron atoms, we can go deeper into the different orbitals. And once we do that, we discover that now, as opposite with respect to the bulk, we have a coupling of orbitals zeta square, so the out-of-plane orbitals. While in the previous case, in the bulk phase, the coupling was also among the in-plane orbitals. And then we understand this as a reduction of, as the fact that moving to the monolayer, those zeta orbital become somewhat able to couple to and actually interact in the generation of the superconducting gap. Now, this is still a work that is very well under development, and we are moving towards studying also iron cyanide monolayer in the presence of a substrate of STO. But this is work for the future, which is very much interesting. But now we'd like to focus on proximity-induced superconductivity in lead telluride lead, which is still within the realm of superconductivity, but it also has a little bit of a different, let's say, view, or it is within a different world because it's about topological quantum computing. And the way that this works is that we are able to build, so the idea is that follow a proposal where we can have quantum devices made of a semiconductor and a superconductor, which can be, which might host Majorana Zero modes. And these Majorana Zero modes can be used to encode and process quantum informations. And these states, these zero modes are perfectly degenerate. They are robust against local perturbation, and therefore can be, thanks to their topological properties, and therefore they can be exploited to perform a braiding operation. Now, I don't want to delve too much into the details of how to perform a quantum braiding. What I would like to mention is that we want to focus on if it is possible and to model realistic devices, and if it is possible to build such hybrid nanowires. So here in this picture, we see a schematic of a typical semiconductor, of a typical device made of a superconductor and a semiconductor. And the picture that we have in mind is actually the one of a full semi-core shell nanowire, where now the superconductor is surrounding the semiconductor in the middle, and then we have Majorana Zero modes at the edge. Now, there have been theoretical proposal and explanation of this effect. For these devices, it has been proposed that we can have two regimes, one which is the trivial regime and another one which is the non-trivial regime or the topological regime. And that the way that it works is that if we have the topological regime, well, in order to have a topological regime, there are a series of requirements that leads to the emergence of Majorana Zero modes, among which we need to have a strong spin-orbit coupling in the semiconductor, but especially a large Landau factor. And we have to satisfy this relationship where the Zeeman energy gap is greater than the sum of the chemical potential and the superconducting pairing potential, in such a way that the electron and the hole that are involved in the formation of Cooper pairs in the superconducting gap, they are spin momentum blocked, and they can either travel to the right or to the left of the nanowire, therefore localizing along the edge. And typical signature of Majorana Zero modes can be the zero bias conductance peak or the 4-pi Josephson effect. However, those theoretical models, they do describe a recipe for how to get Majorana Zero modes, but there are still some open questions where we face realistic materials. For example, what actually happens to the electronic and superconducting properties near the interface of the two materials, and how does the energy alignment between the two materials influence their behavior? So here I'm referring to the Schottky barrier and to the fact that we would like to have the Fermi level to be perfectly aligned between the Zeeman gap and the superconducting gap. And also we would like to prove if superconductivity can be induced or not. And yes, otherwise I would not be here. And what role do strain and electric fields can play in modifying the material properties? So, okay. So I already mentioned that when modeling lead telluride lead, so we want to model lead telluride lead. However, we have to take into account of a series of complication which comes from the uncommensurability of the two systems. So we have to deal with the lattice mismatch. Therefore, we also study the strain, and we want to employ the SIESTA-BdG method to look at the superconducting properties of this heterostructure close to the interface. We start from bulk lead. So bulk lead is a conventional superconductor. If we look at the normal state electronic dispersion, we see that close to the Fermi level, the dominant contribution comes from the p and d orbitals of lead. While when we look at the superconducting state, we recover the conventional U-shaped gap of the order of 3 millielectron volt. and the main contribution comes from the p orbitals. And quickly, we can also have a look at the electronic properties of lead telluride, which is also interesting at the ground state. Now, this is the dispersion of the bands of lead telluride. We have dominant contribution from tellurium p and lead p orbitals. But especially the size of the gap, of the normal state gap, is highly dependent on the strain and on the value of the lattice parameter, and it can span a few milli-electron volt up to hundreds of milli-electron volt. So now what we did was to have two slabs of lead telluride and lead along the zeta direction or 001 direction, and when we have the two materials together, we know that we will have a Schottky barrier effect, or we will have energy misalignment. And if we were to compute the average electrostatic potential across the interface between the semiconductor and the metal, we see that it is quite high. It's of the order of 1 electron volt, regardless of the strain that we applied to the material, because we tested different combinations of strain on lead telluride and lead, and this prevents the energy alignment that would be favorable for the emergence of Majorana Zero modes. So for the emergence of Majorana Zero modes, we would like to have a picture where let's say the semiconductor bands and the Fermi level align closely or perfectly with the superconductor gap. We also, now, since we have such a strong electric field along the interface, we also wanted to have a look at to have information on the charge at the interface, and therefore we performed a Mulliken analysis, and we concluded that we have a depletion of charge on the lead side of the heterostructure, while we have more charge or more electrons on the lead telluride side. So having such a high barrier also implies that the state stabilization is quite strong, and we wanted to quantify this effect. And the way that we did it is that we looked at the dispersion of the full heterostructure. Now the picture is quite complicated because we have a large system and a lot of states. And the way that we decided to simplify this picture is to plot the band structure of the total system, or the total Hamiltonian, made of the semiconductor, the superconducting, and the coupling between the two. And then we, thanks to the localized basis set description of SIESTA, we could also plot the dispersion of the heterostructure with the coupling between the two materials set to 0 to see the difference. And moreover, we weighted in red the projection over the lead telluride side of the heterostructure. So the dispersion of the lead telluride side here in red closely resembled the bulk lead telluride dispersion. But then if you were to look closely to the endpoint, we see that we have strong hybridization because we have a strong splitting of the bands, or strong within the range of superconductivity. And hence we understand that we have a strong proximity effect in the properties of the heterostructure. Okay, now we looked at how the normal state density of state varies with different strain values. So by straining the size of the heterostructure, and also in order to counteract this barrier created at the interface, we tried to apply an electric field in the opposite direction that could counterbalance this effect. But we actually saw that by applying those effects and performing structural relaxation, the results are actually robust. So we do see a robustness of the normal state properties against both the strain and the electric field. Hence, we move to the superconducting state of this heterostructure. And what we see is quite interesting. So first of all, here on the left, we have the superconducting density of state, which is now first of all, the size of the superconducting gap is reduced. So we have lead, which we saw it's as a superconducting gap of the order of 3 milli-electron volts, but now it is reduced to 2.6. And moreover, we don't have any more hard conventional U-shaped superconductor. We have what we call a soft BCS gap. And within this two main coherence peak, we have an induced superconducting gap here, which is very small. It's basically only few tens of few, like 0.6 millielectron volts. And we also saw that the only superconducting pairing mechanism comes from the singlet channel. And we wanted to get more insight into these results. Therefore, we decided to project over the individual layers, which are here labeled from 1 to 15 and from 16 to 26 for each of the layer of the heterostructure. And then what we see is that we do have proximity-induced superconductivity on layer 15 with some lead telluride, which is an unstated interface and then smoothly goes down. The shape closely resembles the shape of the total superconducting dose, while on the lead side, we have more of a conventional U-shaped superconductor. So the way that we understand this is that we have the strong polarization at the interface, and then we have these lead telluride states that are polluting or poisoning the superconducting gap. And this is a bullet point of all the results. And lastly, I would like to mention that this is actually good news for the detection of and the study of lead telluride heterostructure, which can be promising for this application in the realm of topological quantum computing, because the presence of the soft BCS gap implies that we are in a weak superconducting coupling regime, and hence, this is a bit hard to explain, but basically when we have a soft BCS-like gap, we do have the states of the semiconductor inside the superconductor gap, and therefore we can actually see the superconductor. Instead, if we were to have a conventional U-shaped superconductor, then the lead would overscreen or screen completely all the properties of the device, and then you would only probe through the lead. What we can also analyze is the anomalous charge density in real space. And this is also quite of an interesting result. So here I've depicted in red the anomalous charge density on lead side of the heterostructure. Then we see that we initialize the superconducting pairing on the lead side, but then we induce anomalous charge density and superconductivity on the lead telluride side. I had to multiply by 10 to visualize it properly. And we can also cut through the zeta axis, and what we see is that on the lead side is more or less constant with some oscillations, and then it decays abruptly on the lead telluride side with an exponential decay, which was of the order of 14 angstrom. Not only we have the induced anomalous charge density on the lead telluride side, but interestingly, also close to the interface, the homogeneous picture of the superconducting peripotential also fails off, because now we have this anisotropic shape. And when we look at the change of the superconducting density of state with different value of strain, we also see, well, this is less robust, I would say, with respect to the normal state properties, but the picture still remains, or the qualitative picture still remains. And lastly, moving to beyond superconducting density functional theory for quantum transport, what we did was to introduce or to exploit a formalism which allows us to move from conventional quantum transport and rewrite the reflection transmission matrices in very similar to the way and what we did for DFT. We double everything. Now we have new channels, the electron and the hole channel. So now the matrix becomes 2 by 2, and then we can rewrite an expression which was already derived by Lambert for the current in terms of the normal, anomalous, and Andreev reflection. Then we can test this, creating a normal state, superconducting state junction. And actually this is a real simulation of a carbon nanotube. And then we can look at the dispersion. So we have the normal state and the superconducting state, similar to what we've seen before. What is interesting here is that when we compute that we are able, first of all, to compute to to compute the transmission and the reflection function. And then especially we have that the transmission is possible outside the superconducting gap. So here on the Y we have the energy range, and this is the superconducting size. And then we see undirect reflection inside the gap, which leads to the formation of Cooper pairs. And this is still something that we want to work on. But I would like also to summarize and to conclude. So I hope that I was able to convince you that we did we have basically implemented the possibility of computing superconductivity within density functional theory in the SIESTA code, that we can model both conventional and unconventional superconductors, and I showed you some results for niobium, lead, and iron selenide. We've also discussed the proximity-induced superconductivity in more complex devices. And lastly, I just showed quickly the superconducting quantum transport. I would like to thank you all the collaborators, so the other authors and developer of the SIESTA-BdG code, Nils, Arnold, Pablo, Andreas, and Zela. And those are the two references that I would like to mention in the talk, but also all the fundings for funding the project. And thank you all for your attention.
Thank you very much, Ricardo, for this nice overview of your work. So there's time for a question. So if you have a question, please go to the reaction button and raise your hand. So maybe I can start. So in all these calculations, there is an empirical parameter.
Yes.
And so when you compare to experiment, how do you choose this parameter?
Yeah. So so the way that we do it is that, let me go back to the method. It's a lot of slides ago. Yes. Okay. So now the way that we do it is that we have a first guess where the size of the superconducting peripotential is more or less the size of the superconducting gap if I were to compare to experiment. So if I know experimentally that the superconducting gap is 3 milli-electron-volt, then I start with an initialization of the pairing potential, which is like a sphere with a strength of 3 milli-electron-volt. And then I apply the full SCF-BdG method, and then I see what comes out. And then I get a nice dispersion but yeah, the starting point is basically for the strength, at least, of the superconducting peripotential, can be the experiment. So yeah, if I were to compare, if I already know the information from the experiment, it's much easier in a way. So I don't have to try different values.
But if you wouldn't know the experimental value, what would you do?
If I don't know the experimental value, I have two approaches. Either if I'm lacking its conventional superconductivity, then I can compute it via other methods, which would be an option to stay within DFT. And the other thing that you can try that we're actually working on now is to actually test the different values, and then have a look at the results, and then get one that is physical or that you think it's physical. Of course, you don't exactly know well, it is difficult to guess the initial value a priori. So you always need to have a balance between a guess and what comes out. I don't know if that answered your question, because it's a self-consistent procedure. So in a way, similar to all DSCF.
Yes, and so this is also the only, but whether you have conventional or unconventional superconductivity, the only thing that changes there is also this parameter, right?
Yes. Yes.
And so between conventional and unconventional superconductivity, are there different ranges or different values for this parameter that you need, or?
No, not really. So far for the test that we've done now, no, not really. We have not seen a major difference, like a different order of magnitude or something like that. No, not really.
And is it reasonable to expect that if you have the experimental gap and you use that as a first guess, that when you iterate, your final result will be very close to that, or?
Yes, but it's not trivial. It is so definitely the size of the superconducting gap has to be okay. So for example, let's say that you have a as a resulting density of state, a gap that is of the order of 3 milli-electron volt, but lambda can be also 80 electron volts. So that can happen.
Okay, so it's not directly linked to the,
No.
it's not the, okay.
Yeah, it's a difficult question to answer.
Okay. Is there anybody else who would like to ask a question? If you don't find the reaction button, you can also just unmute yourself and ask the question. We're not that many, so. I don't see any further questions, so.
I cannot
Oh, yeah.
find the button to
Valerio,
raise the hand.
okay.
Yes, can I ask? I can ask some questions. So
Go ahead, Valerio.
thank you. About the methodology. So if you can go back some slides to the Bogoliubov question.
Yeah,
So,
these ones.
yeah. One before also. This
Okay.
one. So in practice, you are passing to a formalism in which you introduce a new spinor, this Nambu spinor,
Yeah.
and the two components are an electron and a hole component. Now, in order to form Cooper pair, you have to couple electron and hole in some, for example, unconventional superconductors, cuprates, they say it's a whole Cooper pair. So I don't understand how by this formalism you are coupling electron hole. So you can find a different system. For example, it's called excitonic insulator, in which the ground state is composed by let's say the ground state is not the normal one, but it's a condensate of excitons.
Yeah.
While in superconductivity, you have a condensate of Cooper pairs. So I do not understand how you can find the superconductivity with this formalism coupling electron and hole.
Yeah, the way I know that, so I know this, and indeed the mathematical formalism is quite similar, if not the same, because also there they use I think it's called the back PCS crossover, and then they have these delta matrices for the condensation of excitons. However, the way that I understood it is that actually when you expand, for example, the Bogoliubov operator gamma in terms of the creation and annihilation operator of electrons, the way that we do it is that, if I remember correctly, now the signs of K, when you do this sum, are reversed. And now whatever is for us a hole, it moves in the opposite direction. So we keep the terms electron hole, but actually it's two electrons. It's just because we switch the signs. So I think if you look closely, there are minor differences in the two formalism that we employ, but we do retain this convention of calling the two components electron and the hole, which is highly confusing, but that's the way that I understood it, at least. So it is related to the way that you perform this transformation of basis set from electrons to Bogoliubovs.
So by this format, you can also try
Couple
to study.
particles.
Yeah. Okay. And so you can try also to study systems which are supposed to be excitonic insulators. And so try to see if, for example, you can open a gap in these systems, which is the gap to break an exciton. And
they say that the formalism, the math behind it, it would work. Yes.
Sorry?
The math behind it, the formalism, it would work also for an exciton.
Okay, just a question of a sign. As you say, it's just a question of a sign. So you can get an electron hole changing a sign.
Yeah, probably yes. The only thing that I don't know if it would work is that you would have to check that, for example, for SCDFT, you can rewrite all these potentials in terms, well, you can rewrite everything as a function of the anomalous and charge density.
Yeah, exactly.
What you would have to prove is that for the excitons, you have something similar, like this I don't know.
I see. So, of course, you have to introduce another anomalous density, which is which is not a charge density, because in that case, is uncharged.
Yeah, I don't know how it will work for excitons.
Okay.
But I think it's important to prove this theorem. this
Okay.
DFT theorem. Yeah, it would be important to, yeah.
Okay, thank you.
May I ask a question? I could not find also the button.
Yeah, sure. Go ahead, Ilya.
Okay, well, I have quite a few questions, but let's first try. I'm trying to position this work in the whole business of these heterostructures and the hybrid structure in superconductors. The point is that typically the scale of superconductors, the energy scale and the length scale, energy scale is few millieVs.
Yes.
And the length scales, it's hundreds of nanometers. Yeah, for example, in the lead, the coherence length, if I'm not mistaken, it's about 100 nanometers. And if you want to look on a heterostructure, for example, like the lead and something, then to be sure that everything is okay, we should be able to describe the scales of the order of the coherence length, which is 100 nanometers. And probably this is beyond the scope of ab initio calculations, of the fully ab initio calculations. And for that reason, typically, the people in this business, they're using the effective models, like the quasi-classical descriptions of superconductors, like Ginzburg-Landau, or something like that. And from that point of view, I would say that this is a very nice development, would be positioned as an interface between the microscopics and macroscopics, because the large scales is described by macroscopic theory for sure. On the other hand, the interfaces, like the things which enter the effective theory, like boundary conditions or the effective resistances of interfaces, this is where you could position your business. Yeah, so you can determine effective parameters entering the macroscopic theories.
Yes.
Did you ever think maybe implementing exactly that? Yeah,
Yes,
so,
but now, so we do have say a branch of development that would be related to exploit our method. So reading the PbTe Hamiltonian computed ab initio, and then thinking of doing something very similar or closely related to what is done already for the electronic Hamiltonian. So linearize the system, then create gray bonds and moving higher in dimensions. So that is definitely possible. Also because we are interested in other properties related to this. But what I would like to mention regarding what you said about the coherence length is that I also thought about that, and it is true that superconductivity typically has a coherence length of hundreds of nanometers. However, when I went to compute it for my heterostructure, this method, what I saw, I think it's here, yes, is that if I were to assume that superconductivity is only on this side of the heterostructure, then it decays abruptly. So I mean, on the left side, it will be of hundreds of nanometers, but then here it survives only a few layers. So this was something quite surprising.
So sorry, you mean the what survives few layers? The
anomalous charge. So I'm looking at the anomalous charge density, which carries in a way the coherence of the Cooper pairs, right?
In the semiconductor.
Yes.
Yeah, sure. Because that if it would be an insulator, then it would decay just on a few layers, definitely.
Yeah.
But what is important that everything should depend on the thickness of your superconductor. Right, because that the coherence length of a superconductor, it's a thing which determines the scale inside the superconductor. So in a sense, there will be a very different result if your superconductor is few atomic layers or it is 1,000 atomic layers.
Right.
That is important, right? That so that's you cannot compare. You cannot take the 10 atomic layers of a superconductor and say that this is what you would measure experimentally.
No, that I agree.
Yeah. So in that sense, to describe things correctly and compare with experiment, you should take as many atomic layers as it is in experiment.
I see.
And typically, these are I don't know, 10 nanometers or 100 nanometers or something which is comparable with the coherence length.
Yes, but can I intervene? In this case, so I don't remember the coherence length in lead, but it should be, as Ilya was saying.
I think it's about 100 nanometers.
100 nanometers.
Yeah,
So here
yeah.
you're simulating 100 nanometer, 1000 angstrom.
Yes, absolutely.
Okay.
And
Here,
in niobium, if I'm not mistaken, this is 50 nanometers. Or
in
something.
what?
In niobium.
In niobium. Okay. So so you are simulating a system so a slab of lead, which is less than the coherence length. No, in this case is less than 100 angstrom.
It is okay. It is physically sensible, but it depends. It depends on the thickness. Yeah. So in a sense,
okay. So in this case, the thickness of the system that is simulating is less than the coherence length, and is fine. So my question is, could you find superconductivity in a system which is less, which was
yes, definitely,
size less? Okay.
Definitely,
okay.
Definitely. But this should be the lens which, if you compare with experiment, that should be exactly that lens which you measure. That's the thing. Clearly, you can clearly there are situations when the thickness of a system is less than the coherence lens. It modifies the superconductivity. So the modifications of the superconductivity are sensible. So you can, in principle, describe it, but it depends on the scale. Okay, good. I have another more technical questions. Somewhere you showed the density of states, and I forgot for what it was, and it was asymmetric. Yeah, you said it's noisy. You said it's noisy, but what I noticed that it was asymmetric.
I don't know.
Yeah, exactly here.
Yeah, this one is when we have 100.
Does it mean that there is some? So your implementation does not preserve the symmetry of BdG equations, right?
No, the implementation does preserve the symmetry. It's that the 100 case here, it is so much undersampled that I'm not sampling the energy that would be the peak. I mean, so this is just a convergence issue. But we do have particle symmetry. So the total superconducting dose will always have particle symmetry.
Okay. So essentially your implementation is ensured that it is symmetric. Yeah. So this is something, okay. And then probably okay, another, you said at some point that you include spin-orbit coupling, right?
Yes.
Which is essentially spin-orbit coupling, and can you also include the ferromagnets, that the contact, for example, is a superconductor with a ferromagnet? There is this very active business now, quite fashionable, like the superconducting diode effect, the anomalous Josephson effect, where the combination of the ferromagnetism, the magnetic properties of a material in contact with a superconductor, and this spin-orbit coupling leads to some unusual transport properties. And people always have problems with identifying theoretically the value of the effective spin-orbit coupling or effective parameters entering the effective series, because typically the series are effective low-energy series. And that's where you can kind of contribute to understanding of that.
I'm not an expert on this effect, but for this effect, would I need to also include the magnetic field in the simulation or stuff like that?
Zeeman splitting, yeah, that the
Zeeman
magnetism like in iron, yeah. So if you would have some kind of contact of niobium with iron in the ferromagnetic state,
yeah. Yes, then I think I will be able to capture this. Yes.
So in principle, it is
never thought about it. Yeah.
Or for example, if you have the contact of superconductor with platinum. Yeah. So the recent experiments where people measured or claimed to measure the superconducting diode effect in the contact of superconductor, which is aluminum with platinum. And the platinum carries some significant spin-orbit coupling.
Yeah.
And this leads to some unusual transport properties. So in principle, your implementation is able to capture at the interface the
yes,
spin-orbit
definitely.
coupling.
Yeah, in principle, it is capable.
Okay, and That's essentially very good. Yeah, so that's I would say to me, I would see it as a very good development in that direction, that you can match the microscopic description of, for example, spin-orbit coupling to the effective series which people try to build up to describe this experimental business. Okay, thank you very much. Thank you.
Thanks. Yeah, nice suggestions. Yeah, thanks.
Okay, thanks for the interesting discussion. So there was a question also in the comments, but maybe by Rob Lavrov. Maybe you want to unmute yourself and ask the question yourself.
Sure, thank you for the nice talk. I was just wondering, basically things like cuprates and these other unconventional superconductors have pretty difficult electronic structure for cone-sham DFT. And I'm wondering basically the sensitivity for the underlying electronic structure calculation of the normal state, how sensitive the superconducting calculation is.
So the short answer would be that for simulating properly the electronic, say, normal state structure, we would have the same drawbacks or the same advantages as normal DFT. From the superconducting, how superconductivity might affect the normal state properties of the cuprates, we have never tried to study those systems. So I wouldn't be able to give a quantitative answer on that. Sorry. So because I think your question was mostly like how the superconductivity change the electronic side of these cuprates, right?
I was trying to ask the opposite. Basically, so I saw in your flow chart that you always start with a normal state cone-sham DFT calculation.
Yeah.
So if that is maybe if you chose the wrong functional for the system, or if just DFT is not a good choice for that system because it's strongly correlated, then how is your superconducting calculation affected?
Yeah, no, so it's important that the normal state properties captured properly, otherwise everything screws up. Yes. So that the same drawbacks that you would have indeed, that is the starting point, right? So you want to be sure that the starting point is a good one.
Thank you.
Yeah.
Okay, thank you very much. So it's exactly 3 o'clock, so maybe this is a good point to stop, unless there's some very urgent last question. If not, let us thank again Ricardo. Let me thank again Ricardo for the nice talk, and you all for the discussion. And maybe see you next time for the next ETSF seminar.